The really surprising thing about a whip the first time you hear one cracking is just how incredibly loud it is. And what's more spectacular is the fact that all of the noise comes from the very tip of the cracker on the whip, this little bit of fluffy string here. You'd think that wouldn't be able to do anything, but that's where all the noise comes from. And the key to how a whip works is all down to something called the conservation of energy. So, okay, this is how you crack a whip. This is your basic overhead cattleman's crack. You start with the whip held loosely in your hand with the length of the whip behind you, and then you bring the arm up, you pause momentarily, go back, and then you flip it forward, and that's when you get the crack. And the point is that what you've done is you've put a U-bend into the whip. So when your arm comes forward like this, your arm is stationary, okay? So I've done that. The bottom is stationary, and all of the top of the whip is moving forwards. So because it's moving, it's got movement energy, it's got kinetic energy, and kinetic energy depends on two things: the mass of the thing moving and the velocity it's moving at. Now, the interesting thing about the top of the whip is that as the whip sort of uncoils itself like this, okay, the bit that's moving, because this bit is now all stationary, gets shorter and shorter. So the mass of the moving part of the whip, right until you get to the end, and this tiny little bit of string at the end, which weighs virtually nothing, flips over. So the mass gets less and less and less and less and less, but the kinetic energy stays the same because of the laws of conservation of energy. So if the mass gets less, the velocity has to go up. So as you crack the whip, like this, you start out, and my arm's moving at about 10 meters per second, I've measured it, and you end up with the tip of the whip moving at over 900 miles an hour. Now, to explain that, I need the aid of an assistant, a rubber duck, in this case called Quack. So imagine that Quack is sitting in a pond, and for this thought experiment, your viewpoint is way up there, vertically above him, looking down at the duck. So that when Quack goes bob and makes a little ripple, that ripple is a ring that spreads out around the duck in a circle. And Quack the duck goes bob once a second. So every second makes a ripple which spreads out. So what you see from above is a series of concentric circles. Now imagine that Quack the duck starts to swim forwards, and it swims forwards at the same speed as the ripples move across the surface of the water. So that it goes bob, makes a ripple, and then swims forward at the same speed as the ripple. So it keeps up with the ripple. And then it goes bob again and makes a second ripple. So now you have two ripples in front of the duck on top of each other, and behind they get spaced out more and more. And it keeps swimming, and each time it goes bob, the ripple in front of it gets bigger and bigger and bigger and bigger. And if the duck actually swims faster than the ripple, it goes through that big sort of super ripple in front of it, and you get what's known as a wake behind it, a sort of a V-shaped wave behind it. Now, exactly the same thing happens with the tip of the whip, because the whip makes a little bit of noise as it goes through the air. Just a little sort of whiffly noise, okay? And that whiffly noise is a sound wave. So that sound wave is coming from here, and it's travelling at 730 odd miles an hour. But because this whip tip is moving at 900 miles an hour, it's moving faster. So the same thing happens as happened with Quack the duck. The sound wave in front of the whip tip builds up and gets louder and louder and bigger and bigger and louder. So what you're actually listening to when you hear a whip crack is a sonic boom. There is, in fact, something else going on. When it's moving at 900 miles an hour, what you actually get to hear is a cavitation bubble collapsing. Whoa! So what's happening is the whip tip is now moving so fast through the air that the air doesn't have time to go back round and fill in the gap behind the moving whip tip. So you get a little bubble of vacuum forming. And the sound you're hearing, a very faint sound, but magnified because it's going faster than the speed of sound, is the sound of that tiny bubble collapsing back on itself. So this is a wonderful piece of science, all down to the conservation of energy. Whew. So knowing how a whip works and understanding the physics and the science behind it doesn't make it any less terrifying when you're on the business end of it. You ready?
Yep.
You say that. Here we go. Enough?